Welcome to this explainer. Think about how effortlessly you and I talk to each other. Slang, context, totally messy or incomplete sentences, we get it without breaking a sweat. But computers? They literally require strict, unambiguous code. There's this massive gap between the messy human chatter we rely on and the rigid, mathematical world a computer actually inhabits. So how do we bridge it? How do we build an AI that actually gets what we mean and can reason about the things we say? Well, that process is called computational semantics, and it's exactly what we're diving into today.
Okay, let's start with a super relatable scenario. Picture this. You're building a restaurant recommendation AI for tourists, and someone asks a very simple question. Does Maharani serve vegetarian food? As humans, we instantly know what they want, but for our AI builder's journey, we have to figure out how to turn that string of letters into a formal meaning representation. The system has to actually know what's being asked, dig through its knowledge base, and give a verifiable answer back.
And here's the crazy part. Just think about how many ways we can express that same thought. Do they have vegetarian food? Or are vegetarian dishes served? To us, they mean the exact same thing as our first question. To a machine, those look like completely different languages. If your system's database only stores one version of a fact, most of these alternative phrases are just going to bounce right off it. This right here illustrates why computer scientists desperately need what they call a canonical form. It's basically a single standardized mathematical format that all those distinct, messy human inputs can neatly map onto.
To build this restaurant AI, here is our roadmap. 1. Teaching computers to understand. 2. Grounding meaning in models. 3. Speaking in first-order logic. 4. Mapping complex human events. And 5. Categorizing with description logics. Let's get started.
Section 1. Teaching computers to understand. Setting the rules of the game.
So before we can even start writing code, we need some ground rules. Our meaning representations have to meet very specific computational requirements. The fancy academic term is desiderata, if they're actually going to give our tourists good restaurant advice. Here are the absolute must-haves. First up, verifiability. The system needs to be able to compare a statement to its database to see if it's true. Second, unambiguous representations. Look, if you say, "I want to eat someplace close," the AI needs to know you want a nearby restaurant, not that you're Godzilla wanting to literally devour a nearby location. Third is canonical form, which we just covered. Fourth is inference. The system has to draw valid conclusions about facts it wasn't explicitly told. Fifth is variables. It needs to handle vague requests like find me a restaurant, where the exact place is still unknown. And finally, expressiveness. The language just has to be flexible enough to handle the sheer variety of human utterances.
Section 2. Grounding meaning in models. Connecting words to the world.
So how do we actually fulfill all those rules we just laid out? The secret is a model. A model is a formal mathematical construct that basically stands in for the real world. We call this approach model-theoretic semantics, and it's brilliant for connecting our words to reality. Look at how this maps out. We take our everyday non-logical vocabulary, names and concepts, and we translate them into meaningless domain elements. The patron Matthew becomes just A. The restaurant Frasca becomes E. The cuisine Italian becomes H. But check out how we handle properties and relations. The relation serves maps to a specific pair or tuple of those elements, E and H. For the computer to know that Frasca serves Italian, it just checks to see if that exact pair exists inside the serves relation. It's just pure elegant set theory. Section 3. Speaking in first-order logic, the language of the machine.
All right, we have a model. Now we need a language to talk to it. Historically, first-order logic, or FOL, is the absolute go-to because it perfectly satisfies those computational rules we talked about. So what actually is first-order logic? Think of it as a flexible mathematical secret code. It makes a very specific assumption about the world. It assumes everything consists entirely of objects, properties of objects, and relations among objects. By using it, we can create these little atomic formulas that represent exact, indisputable states of affairs.
Let's look at it in action. Remember our initial tourist question? Does Maharani serve vegetarian food? In first-order logic, that English sentence is translated into a perfectly unambiguous predicate. It basically reads, serves Maharani vegetarian food. This is asserting that the two-place predicate serves holds true between two completely distinct objects, Maharani and vegetarian food.
But let's be real, human requests are rarely that specific, right? We often ask vague things like, find me a restaurant near here, or we make massive generalizations like, all vegetarian restaurants serve vegetarian food. To handle this, first-order logic uses things called quantifiers. That backwards E symbol, that's the existential quantifier. It literally means there exists at least one. It's perfect for finding an unknown restaurant that hits your criteria. Then you have the upside-down A, the universal quantifier. That means for all. It tells the system a rule is true for every single object in the database.
And this is where things get really cool. With these quantifiers, our AI can actually start to think. It does this through inference, specifically using a method called modus ponens. It sounds like fancy Latin, but it's really just basic if-then reasoning. If the left side of a logical rule is true, then the right side can automatically be deduced, even if no programmer ever explicitly told the AI that specific fact.
Let's watch this logic built inside our restaurant model. Step 1. We use a universal quantifier to tell the AI the rule that all vegetarian restaurants serve vegetarian food. Step 2. A totally new fact drops into the database. Leaf is a vegetarian restaurant. Step 3. Boom, modus ponens fires. Because the left side of our rule is true for Leaf, the AI automatically infers a brand new fact. Therefore, Leaf serves vegetarian food. It literally reasoned its way to a new conclusion.
Section 4. Mapping complex human events, dealing with the messiness of life.
Now we had a pretty serious roadblock. While first-order logic is amazing for simple two-part relations, human language is almost never that clean. We're about to deal with the messiness of real life. Consider these two statements. I ate versus I ate a turkey sandwich for lunch at my desk. How do we map that second one into our AI? The problem is that standard first-order logic predicates have a fixed arity, which just means they take a fixed number of arguments. If the eat predicate only has two slots, one for the eater and one for the food, how on earth do we jam in the time like lunch and the location like my desk without breaking the machine's constraints?
The fix for this is absolutely brilliant. It was originally introduced by the philosopher Donald Davidson, and it's called Neo-Davidsonian event representations. Instead of trying to cram every detail into a single rigid predicate, we introduce one existentially quantified event variable. Think of this event variable as a central hub, or like a piece of superglue. We can use it to paste an endless amount of details onto just one single action.
Let's check out the formula for our complex sandwich event now. Instead of rigid slots, it reads like a flowing sentence. There exists an event E. That event is an eating event, and the eater of event E is the speaker, and the thing eaten in E is a turkey sandwich, and the meal is lunch, and the location is the desk. By refactoring our logic to use this event variable E, we successfully capture all the messy, overlapping details of human life without breaking a single rule of our mathematical model.
Section 5. Categorizing with description logics. Building the semantic web.
Okay, so we've got a robust way to represent both facts and complex events. Now, for the final step. When computer scientists build real-world apps, they have to organize massive amounts of these logical rules into a usable web of meaning. To pull that off, they use an ontology. In description logics, an ontology is basically a hierarchical organization. Think of it as mapping out the very DNA of our restaurant world. We create a terminology where we explicitly state what belongs where. For example, a Mexican restaurant is a subset of a restaurant, which is a subset of a commercial establishment.
Description logics give us a really clean way to define all these categories. Take a look at this formula. It defines an Italian restaurant. It asserts that an Italian restaurant is subsumed by the category restaurant, and it intersects with things that definitively have the cuisine Italian. It's a hyper-precise, machine-readable definition that says, to be an Italian restaurant, you must be a restaurant, and you must serve Italian food.
So let's put our AI to the test with a real-world instance checking problem. We drop a brand new restaurant into our database called the Gondolier. We tell the AI that the Gondolier is a restaurant and that it serves Italian cuisine. Then a user asks, is the Gondolier a vegetarian restaurant? Can our AI accurately categorize it?
Well, the AI compares the known facts against its ontology. We explicitly told it the Gondolier serves Italian cuisine. But wait, in our AI's strict terminology, the definition of a vegetarian restaurant uses a universal quantifier that states it must serve vegetarian cuisine, and that is all it can serve. Because serving Italian contradicts that strict only vegetarian rule, the AI's instance checking mechanism arrives at a definitive no. The Gondolier is absolutely not a vegetarian restaurant. Our system works.
And what's truly amazing is that this isn't just a theoretical exercise. The journey we just took to build a tiny, local restaurant AI is the exact same foundation used on a monumental, global scale. Description logics are actually a key component in the development of the semantic web. That is an ongoing effort to formally specify the semantics of the entire World Wide Web using frameworks like the Web Ontology Language, or OWL.
From parsing a basic question about vegetarian food, to grounding meaning in mathematical sets, to wielding first-order logic and event variables, we've really seen how computers learn to understand our world. So I'll leave you with this final thought. The next time you ask a search engine a question, or a virtual assistant books a table for you, how much of your daily digital life is actually powered by this invisible mathematical architecture, quietly translating your messy, beautiful human words into real machine actions? It's pretty wild to think about. Thanks for joining me on this explainer, and keep learning.